Yeah, thanks for attending my talk. It's a pleasure to be here. And obviously, I work for InSpark, as you might guess. We love Apache Spark, so it kind of matches the event very much. A little bit about myself. I'm a data and AI lead at InSpark. And I try to plot a couple of topics that I think care about recently. And basically, I have a background in, as we used to call it, data programmability, basically making sure that data can, be analyzed on a large scale. I've got into the cloud. We work with cloud and with Microsoft Azure. I also have some background in neural networks, so I wouldn't call it generic data science, but some specific aspects of it. So I've been kind of all over the place, and recently I also started caring about, the people aspect and kind of how our team should look like and how to make it high performance, because that's a whole new world, AI. So I'm a bit involved in the human aspect this day. So those are the 4 topics, just a bit about myself. I've been in different aspects of the data business already for 8-9 years, and actually, if you ask me what would be my personal headline, and that would be this: people talk about kind of big data, right, or data problem, and I think it's actually not about a single problem, but it's about many small data or just many data problems. Yeah. So all these conversations that we hear also at this event, right? It's all about data engineering, data science, putting in production, all kinds of things, performance, tuning, etc. So it's not about one little thing, but it's about kind of many things to organize. And actually, in this talk, I want to use probably super counterintuitive running example, which is Rijksmuseum. So the project that we've done at Rijksmuseum in the Netherlands, because actually my goal is I want to emphasize that, the whole kind of Spark ecosystem and the technology and the platform can be also applicable to the context where, you don't have to be shell to run, Spark and Databricks. Because the common conversation that we have, but not everybody is shell, right? And I always give that example, okay, well, Rijksmuseum, I mean, it's a museum, right? It's not something that would be associated with, those kind of big challenges and big kind of intelligent edge type of problem, but we try to make it also relevant there, and I'm going to use this as basically as a running example. So you probably all know Rijksmuseum. It's in the top 5 museums in the world. There are some numbers, 2.5 million visitors. They have a lot of art objects that they have to deal with. So, I mean, but you see in terms of the numbers, it's sort of still all comprehensible. It's not about something that feels like 100 terabytes or something per day. So, however, under the hood, it's just actually quite a regular type of organization. Right? If you look, the public face, it's a museum, it's a, sort of a cultural thing, but underneath, you have a lot of processes going on, which are actually quite regular processes. You have, retail, you have sponsorships, they have pretty large warehouse, capacity planning, ticket sales, all kinds of things. So my point actually here that, those are the things that, regular organization deals with. And, a couple of years ago, actually around 2 years ago, we started these conversations with, what is their data journey, kind of, how do they can envision it. And we came up with basically 3 very pragmatic milestones, which is I, summarize as, first of all, we wanted to consolidate all the data into a single centralized store, which is basically some sort of a data lake. Then, of course, on top of it, the first major milestone would be, actually getting insights out of the data to, optimize all kinds of processes that I mentioned earlier. And then the third step is, really looking into the innovation part, what kind of new ideas can be implemented on top of this data, some predictive models, machine learning, and this kind of things. So it was sort of very natural, right? Get the data first in place, get it under control, start looking at the data, discovering what kind of insights can be get, and then afterwards, kind of the maturity grows and start looking into sophisticated stuff. So I think for the regular organization, well, that sounded pretty logical way. So we didn't run into, super kind of what's the coolest thing can be done with AI or whatever. But we really considered this as a sort of natural move and a multi-year roadmap. So on top of that, what we thought is, and this is the principle that I personally developed, we've been told about this Netflix challenge today, and actually this Netflix $1 million challenge, that is exactly what we want to avoid, because what that was not mentioned in the keynote is that the solution that won that 1 million, Netflix was not able to put it in production. And if you Google $1 million challenge at Netflix, there is a quote says, the engineering effort, we couldn't justify the engineering effort that is needed to put that solution into production. So it worked on some snapshot data, but it didn't really scale on real production data. So, and we didn't want to run into the platform, which, does the kind of a POC or whatever, and then if you go into production or you start growing, you need to rebuild the solution. So that start, grow, scale principle, that was what we were looking at the platform. Because this kind of regular organization is not an organization that's going to invest, several millions in building the big data platform without any business value and use cases. So it should be something that, grows as you need grow, right? And this is where kind of the principle that we used to come up with the platform. So we are basically Microsoft partners, so we only work on Azure, and we've been looking into, how that platform could look like, and this is actually, then the term Lambda Architecture, of course, often comes up as, when it comes to kind of, data platform architecture. So we picked up the Lambda Architecture term and started looking how it should look on Azure, and basically this is what we came up with. In essence, it's very structured view on, from ingestion into, serving and running your models. Not all these components have to be at place at the same time, because if we deal with, streaming data, then we can use event hubs, but not every case has streaming data. So, but this is like a complete picture, and basically, as you can see here, I'm not going to talk about the, the ingestion part and also the serving part. But if you look at the store and analyze, it only has two components, basically. It has the Azure Data Lake Store, which is actually my favorite service in Azure. It's so simple, it is so powerful. I mean, it's petabyte-scale a data lake, which costs like $35 per terabyte. I mean, it just does the job. And Azure Databricks, so we only have two components. And then our aim was, we wanted to feed all that roadmap and all that scenarios into the platform, right? So that is kind of what we came up with. Of course, Power BI often as some kind of a dashboarding tool, but I'm not going to talk about this part. Zooming in a bit into what Azure Databricks is, you will probably see that that slide. There are also a couple of sessions here at the summit about Azure Databricks in particular, but just to make the story a bit complete, it is actually managed Spark offering, which is a fully platform as a service kind of offering. You don't have to deal with infrastructure, which sort of provides that unified workspace to work both for data engineering and data science, and then you can organize your production jobs at workflow. So so far so good. You know, we really try to standardize on the most, getting back, one slide back here, you know, on the most minimalistic, in a way, set of components, because if you work in the Microsoft space, so to say, or in Azure, you know, Microsoft itself has number of kind of reference architectures, yeah, and at some point we've been in this kind of a conversations, yeah, this is possible, but this is also possible, and that is possible. You can use Azure Machine Learning here, and also here, and then Kafka here, and et cetera, et cetera, et cetera. Then we said at some point, you know, okay, that's all good, so it's not about what is possible, but it's about, you know, how it fits, and what kind of technologies we're going to standardize on. So we went for the minimalistic approach. Data lake, it's super simple, and basically then the whole burden then, you know, goes into Azure Databricks, because if we wanted to build all those scenarios, yeah, we only have one component basically being Azure Databricks. So far so good. And then the next question came, you know, how we can actually feed all customer scenarios into that platform that is basically facilitated mainly for the Databricks. And here I started, so that's a bit of a second part of my talk. You know, if you look at the pipelines, right, at something that people tend to call an ETL, or data pipelines. So imagine, so I try to, let me explain kind of the abstraction that I pick here. Basically, at Rijksmuseum, you have several sources of visitors, right? So some visitors purchasing tickets online, some visitors purchasing tickets at the entrance, some visitors are using, for example, a city card, right? And those are fundamentally different types of data, different data sources, right? So they are just really different universes, both technically from the data model, from the information model, etc. And what you need to achieve is, I mean, you need to go sort of on the well, for you on the right upper corner to get your dashboard, so insights into, let's say, how many visitors of what types are actually visiting the museum, right? And if you think about that abstraction, I think that kind of underground map, it's an interesting abstraction, because, you know, there are many steps. So if you consider every station as a kind of some transformation step, then, you know, those three types of data sources, they need to kind of come together at some point, yeah? And let's say the total should be computed at the end of the day, right? So, and if you really look into this whole ATL business, it actually probably even in reality more complicated than this map, because, you know, there are a lot of steps going on to transform this data. There are a lot of dependencies. What happens if, you know, some data is not available, or some failure happened, right? It's really like basically about the trains going on, and, you know, if some train is delayed, then you not get the result. So there are a lot of things happening kind of in between those data sources and the final result that we want to achieve. So, and the question was, you know, okay, ETL fine, Spark job, etc., but how do we kind of get that organized, right? How do we get this under control? Because if we gonna run so many ETL or data transformation pipelines, right? Because one thing that I didn't mention is we also didn't have, you know, like 20 data engineers to run that platform, right? So we have a very limited set of skills and a very small team, and we can't afford, you know, setting up the team that is just constantly kind of debugging and fixing this pipeline. So, and this is kind of, I'm going to refer to the Lambda second part, but in a different context. I'm curious how many of you know that logo. Oh, okay, so only one. actually. That's a logo of the functional programming language called Haskell, and you know it's sort of a big thing in functional language community. But why I'm bringing this up, because actually I want to talk a bit, you know, how do we, so this is where, as the colleague said, this is where really the developer track part of it comes. Basically, that whole problem of the kind of how do we see the pipelines, I started thinking, you know, how do we kind of get under control? And basically, I just want to quickly introduce this, this notion of function composition. It's basically, this picture is from Wikipedia actually. It's sort of, if you have a function f which, you know, takes vector A as an input and produces B as an output, and then the second function which takes B and produces a C, then the composition is, and that is abbreviated as the circle, is that the one that translates vector A to vector C. That's the definition. It's basically applying one function to the result of the other. And just to go a little bit further, I prepared a quick exercise to give you a bit of illustrative feeling how we should kind of look at this and this notion of function composition. You know, if we have one function and the second function, what would be then the, you know, the composition of that function? And so by definition, the composition of that function is the function g applied to the result of function f, right? And if we zoom a bit into details, basically, if you take an input, then the first step, f applied to x, applies results into input plus 1, right? And then applying j to the result of that, it would give you input plus 1 square. So the result of the composition is this, right? It's basically really applying the result of the function, applying the other function to the result of the previous one, right? So the previous one is x plus 1, and the second one x squared, then the composition is x plus 1 squared. Yeah? That's kind of the way to reason about what is the function composition. As if you can see here, and this is where I'm going to jump again back into the kind of data transformation, data pipeline part. It's sort of, you can see that function composition, so if every function is a transformation function, right, of an ETL step, let's say, then we can see all our pipeline as a set of basically functions applied one to each other. And if we now go back to the to my original abstraction, which is then again goes a bit of a high level, you know, in essence here, if we have three functions, they all produce some kind of state, right? And that state, then we apply a final sum function, and then we get to our totals, right? So in essence, you know, basically all the transformation pipeline on again, which we need to feed in Spark, can be seen as a number of transformations, and this state is something that when we save then the intermediate result of that pipeline, so to say, back to the data lake, right? So this way we can really build our pipelines as a set of functions, really as a Spark, PaaS Spark functions that, you know, convert our initial data into some further state, and then we can spot those moments like this state 1 as basically a moment where, you know, you have a dependency between them, right? Because to produce a sum, we need to make sure that all of the data sets already converted into the structure that can be aggregated then, right? And if you think about this for a moment, it's actually a very powerful abstraction, because what it allows us to do it allows us also, as I call it, to reason a bit, to lift up all that story even one level higher and talk about, even like business processes. Because imagine what happens if that data from the entrance is not available from yesterday. Yeah? So the data gets delivered constantly. And if one source is not available, then at the result, if you're not going to do any check, you just run a job or whatever, you're going to get the wrong number of visitors, right? Because one source was not updated. So that kind of structured way of thinking allows us to reason about the flows based on basically a timestamp when the data got delivered. And we need to make sure that, at this S1, the data was actually already converted, and that's the actual data, right? It's really like, basically, imagine we have 3 people traveling to one destination, and they all need to go there. And this state 1 is the one where, they need to get together. And if one train is delayed, then, it doesn't make sense to go to the final destination. Yeah? If they're not going to look at each other and go and arrive, then they might end up only 2 of them at the final destination. And for us, that's not acceptable, because then we're going to get the wrong output. So we need to spot those moments of dependencies between them, and without even looking at the data, but if one train is delayed, so if one pipeline it didn't produce the data for today, then we can't produce the output. This way allows really to feed basically very traditional kind of ETL transformations, whatever you call them, into Spark and into a Databricks, but also get those things under control. Otherwise, you just run Spark jobs without, producing technically correct result, but that result might be produced on the wrong data because the data is not up to date. So having that perspective, it is actually very important to make sure you get really a consistent flow of data, which is actually quite important for applying this kind of technologies to more traditional types of processes. Because if you're in a kind of a data warehouse business or in a database business, there are many mechanisms to ensure all kinds of consistencies, and correctness. But here we have like a completely open world, which is data lake, right? And if we just run our jobs, they can be still technically correct, but they don't produce the right output because the data was not delivered at the first stage, at the ingestion, right? So basically, and that is kind of actually turned out to be the biggest challenge. I try to explain it a bit here, the principles, but we don't have the format to really get into details because, a good thing is that these are all like linear dependencies. I mean, there are not like cycling dependencies. It's really going from left to right, from the data source into the, into the result. And now I'm zooming back into the Databricks story. Actually, this part, what I talked about on the Databricks diagram, they call it multi-stage pipelines. So there is another feature in Azure Databricks that is called like notebook-based workflows. So you can organize your pipelines, by kind of composing different notebooks, and then, everyone can sort of call each other based on the result of the previous one. So basically, that is the technical implementation of the pipeline, but more abstract view is just a composition of the transformation, which can be then put in the Databricks workflows and completely run basically in a kind of a serverless fashion. The only thing that we need to make sure is then we have a job scheduler, also a part of Azure Databricks, so it runs those pipelines, on schedules, etc. So actually, a conclusion is we are on this journey, and our standardization on Apache Spark, it still allows us to move forward. It still allows us to, feed all those use cases, both traditional use cases, into the Databricks component. We don't have to deal with the infrastructure at all. So all that components on the architecture, which I showed, it's a platform as a service. So we don't have any virtual machines, nothing to manage. So we can fully concentrate on, organizing the pipelines and building the functionality, which is, I think, super important. As I said, this kind of function composition perspective, it allows us really to ensure that kind of end-to-end consistency, and then we also use these intermediate steps of the transformation as a way to also, we save them also in the data lake because it is very cheap. We just dump those states, and then we can also inspect the intermediate step just by looking into those saved data sets. So that is, I think, where we are right now, and in a way, going back to the beginning, I think we've got actually full confidence in putting Azure Databricks as a kind of as a central component, and especially this combined with the default Spark, Apache Spark functionality, and those things like multi-staged, workflows, and a scheduler, etc., it actually delivers on our expectations. So thank you very much. That was it from my side. Thank you. And we have...
Thank you, Andrei. We've got about 3 minutes. I know you guys are dying for some cup of coffee, but anybody? Yeah.
Just a question. Why you are calling it a Lambda architecture? I think this is a generic architecture. Every big data problem can be put in this architecture.
Yeah, actually, thank you for the question. The original term of Lambda architecture is basically, the aim of that is to be able to process both the streaming data and the batch data using the single framework. Yeah, and that is actually not something that we invented. It was invented in Twitter, and it was kind of a big deal a couple of years ago because people used completely different technology stacks to deal with the streaming data and separately with the batch data. So Spark that's actually, I think from my perspective, what I mean, we can use one component that covers both types of data, and we don't need to worry about, either that is streaming data or is that cold data. And I think there are a lot of talks about, specific structured streaming and all the streaming thing, or just a traditional one. That is where the Lambda is coming from. So we picked that as something that we thought, that is an established way of doing things in this big data. But the challenge that we had is, we wanted to see that that approach allows us to deliver, those very pragmatic scenarios around, data transformation for our customers, and that's proven to be successful.
Anybody else?
Hi. I kind of would go for the architecture, the simplified architecture that you've got. Microsoft would be quite keen to put Azure DW in that architecture. Is there any reason why you didn't? And when do you think you would need Azure DW in that architecture?
Sure, I'm not quite sure that I understood.
So Microsoft have a reference architecture where they would just use Databricks to do the transformation and then record the results into Azure DW and then do all the BI reporting off of Azure DW. Is there any reason why you didn't go for that architecture? Do you think that offers anything more than what you've got here?
Oh, yeah, so the question is, that is something that you don't see as a default Microsoft recommendation, right, in a way? I think that's my personal interpretation. Those types of architectures, they are very much focused for specific use cases. So they are more focused because here you have some redundancy. I mean, you might need something or you might don't need something. And there they focus on a very specific like use case. This is your problem, this is the solution. Yeah, and if you don't know what your problem is, yeah, if you need to support, you know, kind of the forward, moving forward is your customer, you know, you need to have some redundancy in architecture or some flexibility in a way. And the other thing is we started, and there is a bit of a hidden story behind that, we started this without Azure Databricks being available. So we used Apache Spark, and our custom basically made a Spark cluster. And so that's why, you know, Microsoft had yet something else, and we kept kind of believing, okay, Spark is the right thing. And then Azure Databricks came, and we switched off our custom-made stuff because, you know, we didn't want to actually do the same thing as Databricks does, way more professionally, and we switched to it. So that is another story that, you know, I think in the Microsoft community, the whole Azure Databricks, it's a very new thing, and probably still some experience needs to be gained, and we've been using, you know, even before Databricks, but just Spark. That's why. Does it kind of answer, or perhaps we can do it then offline a bit detail? Yeah, okay, thank you.
We'll give a big hand to Andrei.
Yeah.
We're out of time, but
thank you.